Welcome students, myself Rahul Kotkar, and today in this lecture we are going to discuss about the chapter magnetic fields due to electric current. So friends, in the previous lectures we studied about introduction related to this chapter, magnetic force that is called Lorentz force, Fleming's left hand rule, then right hand thumb rule. Also we studied about the SI units of magnetic field and its dimension. So in this lecture we have to study magnetic force on a wire carrying a current. Okay, so topic number 10.5 that here we have to discuss. So what about this topic? In case of magnetic force on a wire carrying a current, in this case we have to consider the two things. Means two cases here we have to discuss, that is a straight wire, the wire which is a straight, and other one is the arbitrary shape wire, means the wire having any shape. So in both cases we have to find the value of force acting or magnetic force acting on a wire when carrying a current. So let us start the topic. For that we have to just consider a wire having a length capital L. Okay, this wire should be kept in a magnetic field of magnetic field induction B bar, okay, perpendicular to the length of the wire. Means we can keep it like this. Let's suppose this is the wire, and this wire should be kept in such a way that perpendicular. Okay, so how we consider the perpendicular? So for that we have to use the two symbolical situations for representing the magnetic field. Okay, so remember always, when the magnetic field, okay, shown by this cross, okay, so this means that the magnetic field is enters into the paper, means it is a perpendicular to the plane of the paper, and it is enter inside the paper. Means as you observe here, this cross sign will indicates here the magnetic field is entering inside the paper perpendicular to the plane. And in other case, when it is shown like this by a dot, so at that time we consider here the magnetic field is moving outside the paper perpendicular to the plane. Okay, means in this case how the magnetic field is there, it is perpendicular to this plane and moving outside, means towards your face. Okay, so these are the two symbolical representations. Remember, when the cross is there, it means that the magnetic field is perpendicular to the plane of paper, but it enters inside the paper, means moving away from you. While in case of this dot, how the magnetic field is represented, the magnetic field shows here that magnetic field is moving towards you, okay, that is perpendicular to the plane of paper. So in this manner there is the representation of this magnetic field. Okay, and now here we are going to consider in this case, that is the case 1 for a straight wire. In case of a straight wire, what is that? Let we consider the wire having length L, and this wire having a length L should keep in such a way that, let this is the length of the wire. So for our convenience we draw this wire like this. Okay, so here this is the magnetic field experienced by this wire, okay, means what this indicates, it indicates that this wire kept perpendicular to the plane of paper in such a way that Okay, here the dots are to be considered. We consider the dots are here. Okay, means the magnetic field is perpendicular to the plane of paper in such a way that it is moving towards us. Okay, means coming out from the paper. Okay, so let here we consider that L be the length of the conductor. The conductor is having length L. So after that, here we consider that a current is flowing through a wire is I. Okay, so I be the value of current flowing through this wire. Okay, and potential difference applied across it is your V. Okay, so let we consider that a current is flowing through the wire means what? That is the positive charges are moving through the wire from this end towards this end. So while moving they from this point to this point, so they have a certain drift velocity. So they are moving with a drift velocity Vd. So let here we indicate that the positive charge. Okay, so let we consider here Q be the charge moving across this wire, and this will be considered as a with velocity Vd called drift velocity. Now this is the drift velocity of charge, and the velocity of the charge and the current both are in the same direction. Now after that, simply what we consider here, now here there is the presence of magnetic field and this is the motion of the charge. Okay, means here we can apply the both rules. Either you can apply Fleming's left hand rule, either you can apply Fleming's right hand rule. Okay, so both rules can be applicable, but we simply apply here Fleming's left hand rule. Okay, so according to that, what is that? FBI. FBI means what? That is the thumb indicates the force, forefinger indicates the magnetic field, and I represents the current by middle finger. So in this manner we consider the simply here figure. Okay, you can zoom this figure and observe here. Okay, just simply what we consider that this is the charge. Okay, which is here denoted by E, but actually it is a Q as shown in this figure. Okay, now what here we have to consider, we have to consider simply the application of so here this is your charge E, but actually this charge E is the thing what your charge Q, which is flowing with drift velocity Vd. Okay, and this will having a length L. Okay, so in this manner, what is the charge? So charge is nothing but, okay, that is the current multiplied by time, or simply you can define the current is defined as rate of flow of charge per unit time, and from this equation we got this charge is equals to I multiplied by T. So in that case we can written this equation like this: Q is equal to current I remains as it is, and using the definition, okay, drift velocity Vd, or simply you may call velocity V is equal to distance covered by the charge per unit time. So what is the distance covered? That is the length of conductor. So length of conductor divided by time, which nothing but your drift velocity, and therefore we put here the value of time t as a t is equal to L divided by Vd. Okay, and so as here L divided by Vd be the value of charge Q, okay, which is shown here. That is your equation 10.12. Now simply after this, let me consider the force experienced by the charge. Okay, so how much the force experienced by the charge due to the magnetic field, and that can be simply given by applying the Fleming's left hand rule. So according to the left hand rule, let's simply we consider here the current is flowing in this direction. Okay, as the current is flowing in this direction, so we choose the direction of flow of current, okay, using the Fleming's left hand rule. So this is represented by forefinger. So just sorry, not forefinger, middle finger. Okay, just stretch the three fingers of your hand, left hand, in such a way that the middle finger shows the direction of flow of current. What is the direction of magnetic field? Which is in the upward direction. Okay, that is coming out to this paper, that is a perpendicular. Okay, then what is the direction of force? So force due to the magnetic field is this one, so means in the upward direction. So in this manner, this will indicates you the direction of force. Okay, then by applying the simple formula for, that is force acting on a charge, that can be given by charge multiplied by velocity, that is a drift velocity, multiplied by magnetic field induction. So therefore by substituting the value, what is that? Charge can be given by I multiplied by L divided by Vd. Okay, and this is your Vd cross B. Then again we can use this formula in such a way that, what is this cross product? This cross product can be written as simply by writing it as a Vd B sine theta multiplied by unit vector n cap. So Vd get cancel. What we have? I L B sine theta n cap. But friends, remember here, that is the V and B are perpendicular to each other, and so we can replace this theta by 90 degree. And what is the value of sine 90? That is 1. And so what is the finally? We get relation, that is I into L into B. Okay, and what is this unit vector n cap? Which is the unit vector in the direction of force acting due to the magnetic field. So in this manner we get a relation here for simply as a, when Fm is equal to I into L into B. Okay, you can see here this relation. Okay, so we see the relation here, that is F is equals to Fm bar is equals to I to L into B and cap. Okay, so this relation is only for a case when L and B both are mutually perpendicular to each other. But if suppose they are not perpendicular, so at that time this your sine theta remains as it is. Okay, as a sine theta remains as it is, so what happens means the value, that is a theta sine 90 as a, okay, is 1, but now as sine 90, instead of you can write there theta, so your relation becomes again LB sine 90 instead of that sine theta, okay, n cap, and that can be written again as a L bar cross B bar. Means you can simply write L bar cross B bar in bracket, and this is outside I remains as it is. So in this manner, this is the equation of force for a case if the length of the conductor and magnetic field inductions both are not perpendicular to each other. Okay, so this is related to your straight wire. In other case, let here we have to again consider that for the arbitrary shaped wire. Okay, what is mean by arbitrary shaped wire? So that is a wire which having a any shape. Okay, let's look the figure. From figure you get the clear idea about the arbitrary shape. What is the arbitrary shape? Simply it is any other shape, means not a straight line only. Now in this case let me consider the wire of any shape, and here again same situation we observe. The magnetic field is perpendicular to the plane of paper. Okay, actually it is a perpendicular to the plane of paper, but how it should be origin or arise perpendicular to the plane of paper coming outside. Okay, means towards our face. Okay, so in this manner this is the direction of magnetic field. Now to calculate the magnetic field, okay, to calculate the force acting on a magnetic force due to the magnetic field on a wire, we cannot consider the whole wire because it doesn't have a fixed shape. So we divide the wire into the small number of elements. Out of that we consider a small such a element of length dl. Okay, and now here we have to calculate how much force act due to magnetic field on this small element. So for that our formula now becomes, okay, we have to focus on this figure. Now for that we have to use the formula. Okay, recently we studied the formula Fm is equal to I multiplied by L cross B. Okay, but now we have to calculate a small force acting on a small piece of a wire. Okay, so current flowing through it I. What is the length here? Small dl. Okay, as shown in this figure you can observe there this is a small length dl. Okay, then magnetic field will remains as it is of same intensity, that is a b bar. Then in this case what we are considering, so to calculate, okay, this is only due to what, the small piece of wire, so I have to calculate for whole wire. And so for that, to calculate the magnetic field force acting on a wire due to the magnetic field, that can be calculating, okay, by making an integration of both equations. And so that can be given by total force acting on a total wire, that is the integration of small force due to the small elements, okay, multiplied by I into dl cross b bar. So as b is the uniform length, b is the uniform magnetic field acting on the wire, and so therefore we will write the relation I remains constant integration, okay, of dl bar cross b bar, because the value of b and I both are remains the same, they are not changing. As they are not changing, so we keep constant them, but which one varying? dl, the dl may varying here. Okay, and so in such a case means your equation becomes integration of I integration of dl cross b bar, like this. Okay, this is your relation. Now simple, as we consider again so in this case simply here you get a relation for a wire which is nothing but the arbitrary shape. Okay, and for that wire the force acting is given by this formula, that is Fm is equals to this one. Okay, it's a very simple, there is no complications in these equations. Okay, so next point that we have to study, that is forced on a closed circuit in a magnetic field B bar. Now what we are consider here, instead of having a wire, we have a closed loop. Okay, let me consider this loop like this. Okay, say as to A, B, C, D with the loop of the wire, and here we have to calculate force due to the magnetic field. Okay, and to calculate this force due to the magnetic field, okay, let we write the relation. Okay, instead just previously we studied the relation Fm is equal to I into, okay, for a small length of wire dl bar cross b bar, okay, and its integration. Okay, but now here the wire is completely the closed path. Okay, it is what, it is a closed path. Okay, it is not open like this. This is an open circuit. Okay, but it is a closed, as it connected in whole directions. Okay, you may consider rectangle, you may consider loop like this, circle like this. Okay, so all are having a looping, and so these are called as a closed circuits. In this closed circuits, we have to consider the integral over this closed circuit. What this symbol indicates? The symbol indicates that the integral taken over the closed path. Okay, either you should write C also. It is also called as a line integral. Okay, so simply we consider here Fm is equals to integral of I dl bar cross b bar. Okay, so as this integral is over the closed path, then we consider again the magnetic field is also the uniform. So in such a way, again what happens, Fm is equal to, okay, I remains separate, integral of dl bar, okay, over the closed path cross b bar. Okay, now if we consider that this magnetic field is the uniform, as the magnetic field is uniform means B and I are not changeable, only there is a change due to the length of the wire. Okay, and so to have note this change of length, so in case of this, the force acting, okay, suppose we consider that the force acting on this wire get cancelled by this one, and the force acting on this wire get cancelled by this one. So in all cases, okay, if suppose these are the directions of forces, so the force here get cancelled by this one, and the force here get cancelled by this one. In this manner, the total force acting on a wire in a uniform magnetic field in a closed circuit path, it should be the 0. Okay, that's a simple relation. Understood? This is the force on a closed circuit in a magnetic field B. Okay friends, now the next and important topic which may ask for 3 to 4 marks in the exam, which is your torque acting on a current loop. Okay, so what's the given here? Torque acting on a current loop, it is your 10.7th number. So listen carefully. In the 10th standard, you are familiar with the electric motors. Okay, and here in this topic you studied all these things or all this phenomenon. So what is the electric motor and how it should be works, that here we have to study. Okay, so simply in case of that, so magnetic force acting on a current carrying wire due to the magnetic field, and which will be rotate the loop. Okay, and this loop is rotated to the shaft. Okay, so as this loop, okay, as this loop will be starts to rotate about itself, this loop is rotated to, connected to the shaft, and as shaft rotates, and we call the motor works. Okay, that is the simply working of DC motor. So in this manner, we have to consider this DC motor in this case. Okay, we are not interested what is this motor, but we are just going to study the torque acting on this current loop. Okay, so let here we have a figure. Remember this figure, what this indicates? It indicates that there is a north pole, this is a south pole, and we know that the magnetic field is always acting from north pole to the south pole. Okay, so friends, remember that no need to remember or no need to draw these more figures here. Okay, I will explain you simply in a shorter manner. For that, what we have to make the changes in your diagram, that just remember. So in this manner, this is the direction of magnetic field. Let's suppose this is the length. I have to repeat the figure. So it will represent the magnetic field. This is the loop. Okay, this loop is just a break here to make a connection to the battery. Okay, so this loop should be named as a B C D. Okay, so in this manner you name them as a B C D. Let remember here this length should be the L2 and this length should be the L1. Okay, so as this is L1, so this is also L1. As this is L2, so this is also L2. Okay, and now we consider here, if you draw the figure like this, okay, and just mention the forces in this case, okay, as from your book notations, the force acting on this one is BC, okay, is F1. Force acting on CD is F4. Force acting on AD is F2. Okay, and force acting on this remaining AB is F3. Okay, just make the notations like this in your diagram. Okay, so no need to draw these more figures here. Again, one more thing is there. What is this? Here the only simple right hand rule is given to you. So forgot this rule. Okay, don't apply the right hand rule and don't get be the confused, because in this rule what they tells us about the direction of the magnetic field. Okay, right hand rule is there, not a Fleming's right hand rule. It is simply the right hand rule, and in this right hand rule the pointing the figure, that is a middle finger, okay, by the direction of magnetic field, and so it somewhat get confused. And so for avoid the confusion, what we are doing, we avoid this rule, we simply use the Fleming's left hand rule. Okay, now means these corrections you have to make in your diagram, okay, and as well as in your whole topic to study and to remember easier. Okay, again I will tell you some important things. Okay, what are that? Simply there is no need of this diagram. I just told you there is no need of this diagram, and so there is no need of these equations also. Okay, what is that? I am going to explain, and thus while explaining you get the answer why I am telling like this. Okay, so friends, simply, so remember the figure. Okay, what is that? This is the north pole, this is the south pole. Okay, this is the magnetic field. And remember friend, while drawing this diagram, no need to draw such a more lines. Okay, just draw two lines and represent them simply as a B bar. So what is this? It will gives you the idea about the diagram. Now in this case, what we can consider, we consider a wire loop ABCD, okay, wire loop, current carrying loop, okay, ABCD is of the rectangular shape placed in the uniform magnetic field in such a way that, okay, the segments AB and CD are perpendicular to the loop of the magnetic field. Okay, are they perpendicular to the magnetic field? Okay, just remember, this is a rectangular loop ABCD, okay, in which what we can say, these are perpendicular. Okay, so here the north pole, here the south pole, like this, and so they are perpendicular to the magnetic field. Okay, then this BC, as these two sides are perpendicular, means what, this BC as well as AD are parallel to the magnetic field. Okay, now apply simply the right hand Fleming's left hand rule. Okay, so in such a manner, again remember, this is the length L2, length of the loop should be L2, this is the length of the lamp, L1. Okay, so as this L1, this is also L1, this is also L2. Okay, and what are the forces we discuss later. So after that, as you apply the Fleming's left hand rule, so what you observe, okay, initially as shown here in this diagram, what happens, the current enters from this branch, move like this, okay, and comes out from this one. Okay, so remember, means what, the line we just talk about this now, AB. Okay, so in case of AB, current is moving towards you. Okay, just stretch the three fingers of your left hand, okay, as they are mutually perpendicular to each other. So just FBI, according to that, current I is acting towards your side, magnetic field is pointing towards the right side. Okay, so what is the direction of thumb? Thumb is moving in the upward direction. Okay, so as you observe in this diagram, the FM force to the magnetic field is in the upward direction. Is that clear? Okay, so this is the one force which acting on the side AB. Okay, then in similar manner you can say about this one also. Again apply the Fleming's left hand rule to this side C and D. Okay, as you observe, what is this, it is acting in a downward direction, FM. Okay, as you observe here, so FM is directing in the downward direction, you can observe here. Okay, so in this manner these two forces are acting on this wire and the sides of the given loop. Now in this case, okay, so in this case we have to be consider, okay, means as you consider in this manner, okay, that's I'm going to explain here. So in that case you must be avoid to write or read to write all these things. Okay, no need to read this thing also. Okay. Then next important point here that you have to note, you should avoid this figure also, avoid this 10.11 figure also, and as well as this 10.12b also. Okay. Now the second thing, you must avoid to write this also. Okay, this one also there is no requirement to write also here. Okay, now what you have to explain, so simply, as this is the loop, okay, this is the magnetic field due to the north and south pole, as this direction, okay, A B C D, so as this BC and AD are parallel to the direction of magnetic field. So as we have a formula, what is that? Fm is equal to, okay, according to this formula, IDL, okay, or you simply write the IL B sine theta n cap. So what is this? This L and B, length of the wire and the magnetic field, are mutually parallel to each other. They are parallel, means they have angle 0. So sine 0 has value 0. As this is 0, so whole becomes 0. In case of anti-parallel also, in this case, the direction of magnetic field and the length of the conductor are mutually they are anti-parallel to each other. As they are anti-parallel, means they have an angle of 180 degree, and sine 180 degree have a value of sine 180 degree again have a value of simply as a 0. Okay, and so therefore what we can say, as it have a value 0, so simply what we can say, this whole value becomes 0. Okay, means this force and this force having a 0 value, or they are equal and opposite, and so cancels each other. Okay, because they have a 0 value. Okay, means no need to consider whole these things. Okay, it's very simple, just you should write this relation, and according to this what we can say, the magnetic field is parallel and anti-parallel to the length of the wire is a parallel and anti-parallel to the magnetic field in case of AD and BC respectively, and therefore force acting on them due to the magnetic field is 0. Just write in the sentence form also. Okay, either you can represent it like a equation. Okay, then next point. Okay, we talk about this one. Okay, we talk about this loop side like this one and this one. Now we have to talk about this side AB and side DC. Okay, so while talking about them, now what is that? Just I am going to explain now. Okay, just I told you what you have to consider in this figure. In this figure you have to consider that there are forces acting on this one. Okay, what are the forces acting here? So you must have to consider this loop. Okay, and in this loop what you have to consider, the forces acting AB. On AB you have to consider the force F3. Okay, just keep this thing in your mind and just apply here. This should be your F1, opposite to that F2. This is F3, so this is F4. Okay, BC D. So remember, these forces cancels each other because they have a 0 value. So we have to talk about only these two forces, and which are represent here FM, FM. So we call this one as a F3 and this one as a F4. Okay, now I will rub it again. So next point. So for mathematical equation you just have to consider, okay, so in this manner, this you have this figure. Okay, in this figure what you have to consider, the force acting. Okay, and we just drawn their direction also. This is the direction of current, okay, towards yours, means this one side, direction of magnetic field. Okay, so as this is the direction of magnetic field, then we can calculate the direction of force. So what is the direction of force? The direction of force should be the in upward direction. Okay, like this. So according to the Fleming's left hand rule, remember friends, I am using here Fleming's left hand rule. Okay, and as I am applying this Fleming's left hand rule here, so what is that? According to that, you have a direction of force in the upward direction. Okay, so this is your axis of rotation. In similar manner, for the current flowing in the branch CD, okay, in case of this branch CD, what you have, the direction of force, current having this direction, magnetic field having this direction, and so according to this Fleming's rule, the direction of force is in the downward direction, okay, which is your F4, and this is your F3. So these two forces acting in the upward direction and acting to in a downward direction, let this is of F4, this is the F3, okay, about the certain axis of rotation. So these two forces are acting, okay, in the equal, okay, these two forces are equal in magnitude, okay, and opposite in direction, and we know that the two forces acting at a point on a wire, different point on a body, okay, having equal magnitude and opposite direction, so they forms the torque, means torque is developed on this wire. So there is a formation of torque on this wire. Okay, so as these two forces are acting here, which are equal and opposite, and so they forms the torque, and so what happens, this coil will be turned about the axis of rotation. Okay, and now friends, remember, so this is what, this is your movement arm, and as you observe this diagram, what is this? This is nothing but your length L2. Okay, I just explain you in the initial case. Okay, let here you have to consider this length as a L2. So what is the force F2, force F3? The force F3 should be here. F3 is equal to, according to the simple, I into L into B. Okay, sine 90, and sine 90 having value 1. So I will just write here F into I into L into B. But what is this length? The length of this side should be the L1. Okay. So what about the F4 again? F4 should be the same. Current I multiplied by length is also L1, and this is the magnetic field B. Okay, means these two forces are equal in a magnitude. Their magnitude is the same. Length is same. Okay, current is same, magnetic field is same, so magnitude of these two forces are the same, just they are opposite to each other, and so I am not consider here the vector form, just consider the magnitude. Okay, then what about the next, that is a torque. So to represent the torque, okay, now to represent the torque, we have the formula, torque tau can be given by R multiplied by F. Okay, R means what? Moment arm. So what is the moment arm here? This is the moment arm. Okay, and what is this value? This having value, the length is your L2, half of that, half of the length. Okay, and at actual it is a perpendicular distance. So for considering that, simply, if suppose this distance is not exactly perpendicular, suppose it is exactly perpendicular, then we just take a half of the length 2. Okay, but if suppose this distance is not exactly perpendicular, it is somewhat like this. Okay, if it is a somewhat like this, then here you have to consider the perpendicular distance, means you have to draw the perpendicular from this one. This is the angle theta, as this is angle theta, you have to calculate this one. Okay, means to calculate the perpendicular distance, this one. Okay, and so to calculate the perpendicular distance, we use the trigonometric in this case, and we get the value of this one as a, so what is the value of this torque? Torque acting here is equals to R. R means half of the length. Okay, and what is the half of the length? Half of the length is your L2, half L2. Okay, and for considering that particular direction, we consider here sine theta. Okay, how it should becomes according to the, if the both forces are not exactly perpendicular acting on a wire, so at that time we have to consider the angle and multiplied by force. Okay, so in case of both the forces, okay, I called it as a torque acting on this wire, which is a AB, so F force AB, okay, you may call F3 also. And so just write the whole relation, and you can just make the arrangement here like this. What you can mention, you just mention total torque can be given by torque acting on AB plus torque acting on CD. Okay, so torque acting on wire AB, that is 1 by 2 half, okay, 1 by 2 L2 sine theta. And what is this force? F3, or you may call force acting on AB, that is what I into L into B, L1 into B. Okay, this one IL1 B. In similar manner IL1 okay B for next, that is a CD. And what is this? Half into L2 sine theta. Okay, you can observe here. So by substituting these values, what you get? You get simply the value, that is I into L1 L2 B sine theta. Okay, this is for a single loop, torque acting on a current carrying loop due to a single loop, that is I into L1 L2 B sine theta. But if suppose the coil having a made up of number of turns, so at that time you have to just multiply torque toe dash. Okay, what is that? Toe dash with the total torque acting on a number of loops. Okay, multiplied by torque acting on a single multiplied by number of turns. And in this manner you have this relation. Okay, what you can do in this relation, either you write this here also and here also. So as you know that this is the wire having length L1 and L2. Okay, so what is that? L1, length multiplied by breadth, is called as a area, and so you should mention here instead of L1 L2 as a. So Ni into A into B sine theta be the total torque acting on a wire. Okay, so after that you get this relation in this case, and this can be applicable for all the cases. Okay, means you can apply this, okay, formula for all the case of flat and planar coils, okay, irrespective their shapes in the uniform magnetic field. So friends, in this manner, this is the topic, okay, which gives us the torque acting on a current carrying loop. Okay, so friends, please study carefully, and if you have any doubt, can be asked me in the comment section. Thank you for watching the video. Thanks.